Good morning, everybody. So my name is KD, and as Kevin introduced, I am CEO of a company called Kuloli. You might have heard of us in the past couple of years. When we launched the first ever NB-IoT system on the 708 spectrum a couple of years ago in Jacksonville, Florida. And since then, a lot has happened in the past year, despite the pandemic, and particularly wanted to talk about three interrelated topics: 5G-IoT, 5G in general, and 5G-IoT in particular, and then the definitions and the terminologies that what folks are using and what they mean, and then the phenomena called edge compute and how that's an important component in realizing the use cases in the IoT world. And then towards the end, we'll talk about a couple of real-world examples of these 5G IoT and edge compute combined deployments look like. And then at the very end, I want to spend some time about three things, which is number one, what is the definition of private IoT is, and then secondly, the compare and contrast with some of the LP-WAN technologies that are out there, and then I'll wrap up with a couple of points about the vertical integration and the service level offerings that go hand in hand with 5G IoT. Right, so let's get to the meat of it. So we in the industry use the word 5G pretty liberally. The word gets tossed around in various contexts by different segments of the industry. So I want to spend a few minutes here setting the formal definition as someone who as a company that has spent a lot of time in this domain. I wanted to make sure we explain to the world what this really meant by this. In the presentation before us, Bob and Prakash talked about the 3GPP and the standard setting body. And I wanted to kind of pick up from where they left in terms of how 3GPP today is defining 5G. So the 5G definition of 3GPP is essentially a three-legged stool. It is an umbrella terminology that captures three distinct technology groups. And I'm going to briefly spend a little bit of time on each of them so that there can be compare and contrast and people know when we say 5G IoT, what is meant. On the very top is what is called the enhanced mobile broadband. So that is when for most people in the industry, when they say 5G, that defaults to them. So that is an evolution of what in the utilities world we call broadband. So the broadband that started on the 4G side is evolving into the 5G. The big change in the 5G version of it, they took the LTE and added flexible numerology in terms of channel spacing, carrier sizing, and overall occupied bandwidth. And they made some physical enhancements to higher order modulation. So the net result of that is you have a higher peak throughput and a little lower latency than LTE, but foundationally it's an evolution of LTE. So that's EMBB, so EVO Enhanced Mobile Broadband. That's at the top. That's the first leg of the three-legged stool, of the 5G stool. On the lower left, the lower right-hand side, is one of the new ones that got added in the 5G specifications. And that's a loaded acronym called URLLC. That stands for Ultra Reliable Low Latency Communication. So what that really means is that for the first time they introduce a millisecond or in the range of milliseconds, a guaranteed latency way of doing physical layer and link layer implementation, and also reliability guarantee levels. So that is new. It's still not fully complete yet, specifications-wise. I think there's another round to go. And that's meant for automotive applications, so roadside access points to have vehicular collision avoidance and all of those things. As you can imagine, they require extremely high reliability and very low latency. It is also meant for Industry 4.0 manufacturing automation, factory and manufacturing automation that requires controlling the manufacturing processes within a high reliable millisecond range of kind of latency managers. So that's work in progress. It's still not fully done yet. The lower left side is where I'm here to talk about. And that is the third leg of the 5G stool. And it is officially called massive MTC, massive machine type communications. In that third leg of the 5G stool is the two technologies there, which are both, just like EMBB, it came from LTE. It started under LTE under the name NB-IoT and Cat-M, LTE-M. M stands for machine type communications. So both of these things have been incorporated into 5G, and they are going to live under the 5G NR standardization process for a long, long time. And they are the official machine type communication for 5G going forward. So NB-IoT, the acronym you have heard, stands for Narrowband Internet of Things. LTE-M stands for LTE for machine type communications, now part of the 5G for machine type communications. Synonymously also used as Cat-M, category M. Again, M stands for machine type communications. So anytime you see Cat-M and LTE-M, they are more or less synonymous. There's an important distinction on the physical layer side, but I won't dwell on that for the purpose of this presentation. They are synonymous. So that massive MTC is meant for the use cases that I'm going to talk about today, which is a latency-tolerant telemetry applications for sensors, actuators, most of the SCADA type applications that this utility audience is more familiar with. So that's very important to point that, because it's meant to have a low-cost endpoints, long battery life, and long range coverage. So that's the important distinction there. And by the way, if anybody has any questions, feel free to interrupt me, because if it's a short question, I will answer right away. If it's going to take some time, I'm going to wait until very end. Yes, go ahead.
What kind of bandwidth does it give?
It varies. Can I answer that towards the very end? I promise I'll get back to that. So, because I'm going to touch on that point in this slide, so that's why I want to go through the whole thing and come back to the question at the end. So, characteristics of 5G IoT. First thing, this is not broadband. As I mentioned earlier, in the three-legged stool, broadband is addressed by the first leg. In this leg, the third leg, we are not talking about broadband. It is very important to distinguish that this 5G IoT is meant for many other use cases that are not covered by broadband. So what are those use cases? Telemetry traffic profile. So occasionally you send a little bit of data every now and then. You are latency tolerant, but you want to have lots and lots of these devices. That's the key point. You want to have low cost devices, but in a very large number. Something you typically do not do and cannot do on broadband sense, because either cost-wise, spectrum-wise, coverage-wise, it's not feasible. And they are designed to be battery operated in many cases. So for that, there are a lot of physical layer and link layer capabilities that are introduced in NB-IoT and Cat-M that is meant to enable these long life battery operated devices. That is everything from the channel bandwidth to sleep cycles to power saving modes. There are a lot of capabilities introduced in the specifications that's going to enable, that has enabled these battery operated devices. Long distance, the default range can come up to 40 kilometers. With an extended range, capabilities can cover even farther distances, assuming the link budget and other characteristics allow for it. So that's a big deal, because now you can have a much larger intersite distance between tower locations and have a network topology and a network deployment that's economically far more attractive, particularly if you want to do a private network. So this goes hand in hand with the push towards a private networks for enterprises, utilities, critical infrastructure industries. This is also a key enabler for that. And the flip side of that is because you have a robust link budget with 164 dB maximum coupling loss, in addition to a lot of the coverage level with a lot of repetition and other encoding techniques that will enable a deep window coverage, which is also again plays into many of the utility use cases. Last but not least is that I get this question quite often when I talk about it for folks particularly used to some of the mesh network technologies, particularly in the legacy AMI networks. There is no such thing as hopping and meshing or relaying in this one. It's strictly a long-range point-to-multipoint in a typical hub and spoke design. There is no other entities or nodes or relays required between your endpoint and the network. And that's, I'm going to show you a network, the big picture in a minute. All right, so let's look at how it looks like typically. And it is it's somewhat a simplified version, but it gets the main point across. So going from left to right, your sensors and assets gets attached to this 5G-IoT endpoint. And these things are increasingly becoming very compact and very small, and increasingly downward price pressure on the cost and the price point. And if you want to see how some of them look like, come by our booth. We have a couple of examples if you want to take a look at what the endpoints looks like going forward basis. So lots of interesting form factors and attachment options emerging in this on that side of the industry. So, and the other aspects of these endpoints is an edge compute capability. And I will define what that is in a minute, but it's important that these endpoints, these next generation 5G IoT endpoints have capabilities to do edge compute functionality. So from there, you have this long range 5G IoT link. And typically that looks like a cell tower, and in fact it is typically the antenna is a cellular antenna, panel antenna, and then on the base of the tower there is an NB-IoT or a Cat-M base station which talks to the cloud entity that will be the peering point for many of the utility backend systems. So typically, in the cloud compute will be the interface that talks to the legacy systems using the existing protocols and handshake. So whether it's a Modbus TCP or any of the legacy interfaces that SCADA platforms or IoT platforms use, they will be talking the same language, existing protocols. So the idea is that you have no impact on the backend, very little, minimal impact on the backend, and you fully modernize and upgrade your front end. So that's kind of the best way going forward, because we get this question all the time when we talk to our customers, is that, oh wait, what do I do with my SCADA backend? What do I do with my IoT platform? The good news is that for the most part, you can keep it without any change and still modernize and introduce 5G IoT in the backend. Right, so what's edge compute? First of all, we have to define what the edge is. So you hear the word edge compute and edge appliances and all many different incarnations of that definition. If you are talking to AWS, if you're talking to Azure, if you're talking to most of the network-centric vendors and suppliers, they are talking about pushing the edge. Let me go back again. Pushing. Think of the tower as the edge. The base of the tower has an appliance, would have an appliance, that would be the edge for that. Whereas in the case that we are talking about edge compute, is the edge compute is extended across the link on the other side to the endpoints. So that's the definition of edge for the purpose of edge compute in this context for utility use cases. So it is very important to internalize this, because that's not the most common definition of the outside in the industry today when we talk about edge compute. For us, edge is all the way to the radio link, because for the utility and critical infrastructure use cases, we see that need to have that on the edge for many different reasons, because including the existing, some of the supporting existing soft PLC function, controls and measurement functions that's needed to realize, to realistically deploy some of the use cases. So the endpoint will be continuously reading quite a voluminous data from the sensors or the assets. An example would be is that if you are measuring a water pressure monitor, or some kind of a fluid pressure monitoring system, you can sample the data very, very frequently to make sure you don't miss any anomalous events. But you do not need to transmit that data back to the cloud all the time. And you can build in some intelligence and the edge compute capabilities so that you have a selectively and maybe a certain periodically, certain periodicity basis, you can send the data back to the cloud. So the lot of data processing in the front end and a very selectively using the radio link. So what's an example of those things, right? So for example, you can, I mentioned one example of the water pressure monitoring we'll talk about in a minute. You can specify lots of rules. You can set up a lot of templates in terms of what constitutes a message back to the cloud. So whether it's you want to have a thresholding, you're going to have an averaging, you can have a periodic reporting, all of that can be done. And then on the other side, you can also receive downlink control messages, assuming there is some certain latency tolerance to that, to implement some what's traditionally a soft PLC kind of thing, turn on and off, or maybe change some of the register settings and so on and so forth, can be also done on the downlink side. So it is a bidirectional link, NB-IoT is bidirectional, and we want to exploit its capabilities to make sure that you implement some real-world use cases. And as I mentioned earlier, the wireless link, the net result of this paradigm is that now you can get away with a very NB-IoT or a Cat-M kind of radio link and be very efficient about how we use the link, and that is key. This is where the economics come into play. For a utility to implement a 5G-IoT use case in a large number of devices, and not to be not to have a need to have a large spectrum, and be able to have either a NB-IoT or a Cat-M kind of spectrum, and be able to economically have a feasible solution, that is key. So that's where the edge compute and the system come into play. And important point is that the counterpart to this is the cloud compute component is equally important, because that obviously, as I mentioned earlier, has the legacy SCADA interface support and preserving the legacy investment without with a very minimal disruption to the existing workflow. And last but not least, this goes without saying, the net result of this is you have a massively scalable solution. You can heavily digitalize your front end, you can add sensors, you can add a lot more assets to monitor without breaking the bank. So I want to emphasize, so people talk about 5G-IoT, people talk about IoT, people talk about edge compute. The key is to bring them together in a way such that it makes economic sense, and at the same time it's solving some real-world utility problem. So the other terminology I want to briefly spend time talking about is the Scala IoT, and it goes hand in hand with the previous 2 points. So essentially the one I just said earlier, which is to have a very minimal impact on the back end, but completely change the front end. So you take the best of the both worlds. You have the SCADA model intact, yet you have the 5G IoT on the front end. And this way, we found out many of our customers we speak to, they find that this is probably the best way forward for them, because the SCADA is foundational for anything that happens in the utility world, and it's going to be for the foreseeable future. I don't see that changing at all. So how do you keep the SCADA model and still bring 5G IoT into your communication network and the solution portfolio? So we think, so if you, this doesn't just for utility, this applies to many other adjacencies as well, and keeping, modernizing the front end and bridging the 5G world with the SCADA world. All right, so a couple of use cases I want to spend some time going over it. The first one is a water pressure monitoring system we have been operating in JEA, Jacksonville, Florida. So the problem statement there was the customer had a need to measure water pressure reliably and securely beyond the SCADA facilities. Long term, that's where they wanted to go. What I want to show is an example actually installed inside the SCADA facility for a side-by-side comparison, but the long-term need is to go beyond their existing SCADA facilities, which meant it has to be battery operated, it has to work on the entire service territory where they may or may not have SCADA coverage, and they may not have the need to start monitoring water pressure everywhere. So they're exploring the NB-IoT based system as a going forward solution. So it's a private network built on upper 700A block NB-IoT network, and it has edge compute capable endpoints with the water pressure sensors attached to it. So that was the solution for that particular problem. And pictorially speaking, you can see on the lower left side the pressure sensor. It's a current loop 4 to 20 milliamps sensor, and then on the other side it comes in to the edge compute that's inside an enclosure box. This is one of the first generation edge compute. We have a second gen version of that we have in our booth later this afternoon. Come by, we can show you some examples of that, what it looks like going forward basically. So this is the first generation one, and this is just typically what the measurements looks like. Currently, I think we are doing time averaging or time reporting. We could do a lot more, thresholding and alarming as well going forward basis, but the idea is to prove the fundamentals for this use case and build on this going forward as we go outside of the SCADA facilities and coverage areas. So we think this is a foundational use case. This is applicable not just for utilities. We are also working in other adjacent segments, oil and gas, energy, distributed energy, many other related, and the municipal water districts and so on. So this applies to quite a lot of other use cases, the basic idea. Second use case is the distributed energy resource management. This is an emerging category that's it's not maybe not directly related to some of the things that you would do typically, but it is we see that's another emerging need. So the problem statement is the need to have a secure, reliable, a cost-effective system that is legacy SCADA compatible. But they wanted to start monitoring and controlling of the DER resources. So they have a bunch of options here. They have a public cellular option. They had they start now looking at a private network option, and they have a bunch of proprietary options as well. The security and reliability factor came to a forefront in the recent months after some of the incidences that happened where security was compromised recently in one of their peer entity, and then they had a reliability issue during a critical event earlier this year. So both of those woke them up to the need to have, not only they want to have a system that's going to be compatible with the existing SCADA, but they want to be able to make that secure and reliable. So those two requirements came to the forefront as a result of that. So the solution that we are putting together for these folks are using a 5G-IoT private network solution. So it is a dedicated network with edge compute endpoints supporting CAN bus and Modbus I/O. The reason it is solving the security and reliability aspects is because it is a separate network. There is no other broadband traffic. It is not sharing with the public cellular. It is purpose-built, and it's going to be there for their use throughout this lifetime. So that's number one. And then the edge point capability is becoming very important because As I mentioned earlier, they're going to be measuring lots of data through both Canvas and the Modbus IO, but vast majority of the time that data is not going to go back to the cloud. A summary version or as needed information is going to go back to the cloud, and thereby being very efficient about how the radio link gets used. So pictorially, you can see the resource in the middle, and this is one of our second generation endpoints that we have that's coming up. That's going to go into a radio resource, a distributed resource, energy resource like what as an example of this. The actual implementation is different. We're not allowed to share that, but the idea is the same. It is going to go into a DER resource, and these resources are distributed across across a very large footprint in a very large state. It requires a wide area coverage. So that's a good fit when anytime you look into a network design that meets the topology of the endpoints, the resources, the economics come into play as well, right? If you want to have a private network, but you need to have a very large area to cover with, the economics is important. So the two anchor technologies in 5G-IoT, the NB-IoT and Cat-M, play very well into that scheme of things. All right, so now we are going to spend the next 10 minutes or so talking about the three most questions I always ask, get across. In addition to the throughput question the gentleman asked, I will come to that in a minute, but there are two things. Why do you need a private IoT network? Why have a private 5G IoT instead of going with a public cellular? So it comes down to basically three distinct points there. First of all, as a utility, do you want to have full control over the technology life cycle of your solution and the deployed assets? Right, number one. Because under any circumstances, AT&T, Verizon, or any other public cellular is going to guarantee that. Even for the very large IOU, they're still not going to do it. So that becomes a big, important strategic determining factor. And then second is, do you want to have the reliability? Do you want to have an additional level of reliability that that needs to be put in an SLA basis? So whether it's a application level or a service level SLAs. Again, public cellular is not going to do that. And so you, if you have a natural disaster, if you have a critical event or a crisis event, do you want to stand in line next to a broadband traffic or a consumer traffic that goes through the same network? Those are the decision points, key determining factors that makes the decision one way or the other. And the last point is security. 5G IoT security framework, whether it's a private network or a public network, the underlying, the first two layers are exactly the same. So you have that security that comes built in, whether it's you're doing private or public. But the big difference is that you have your own license spectrum, you have your own complete separate traffic. You're not mixing with anybody else's traffic. And as long as you have your network in the same trust zone as your cloud or your backend IT systems, you have as much of a protected system as you can currently have. So to the extent that security aspects are a big important factor for you, then the decision swings in favor of having a private network. And the last point that is outside of the three main factors is the economics of it. Until very recently, the cost factor was a big variable in terms of killing any such initiative. So Bob mentioned earlier in the first presentation this morning, 8% of the cost is spectrum, and remaining 92% goes into many other things. That shows the huge inefficiencies still exist in the industry in realizing this solution, putting them into practice for a utility. So what 5G IoT, and I'm going to mention that as a third point later on, what they have now gone is that now you can vertically optimize, a fully optimized vertical stack that is purpose built for the IoT technologies. So that enables you to, for the first time, your cost basis is coming to the point where it is not that different from a public cellular cost option, which has never happened before. So NB-IoT, as Bob and Prakash mentioned in the first presentation, takes only about 200 kilohertz at a time, what is it, carrier. And Cat-M takes, start with 1.4 and builds up from that. You do not need a big broadband spectrum. You don't need 3+3, you do not need 5+5, you don't need 10+10. So now you can start as a lower cost basis on the spectrum side. You have a fully integrated, vertically optimized stack, and the system solution providers coming into the play, and a shameless plug for us, Puloli as well. But that with those two factors coming into play, now for the first time as a utility, you have a economically viable option in addition to the meeting your technical and business operational needs. So those are the big factors that are playing in favor of having a 5G IoT, private 5G IoT network. So second thing I want to spend a little bit of time dwelling on is comparing with the other LPWANs. So LPWAN is an acronym, stands for Low Power Wide Area Networks. It is a term that's as an umbrella term that captures the essence of wide area IoT technologies. So in addition to the 5G IoT and the LTE, original LTE, previously under LTE, the NB-IoT and Cat-M, the other two big ones are LoRa and Sigfox, and there are a few other proprietary technologies in the past, and also just to be totally inclusive, Bob mentioned a narrowband WiMAX variant in the IEEE 802.16 series. So all of those come under an LPWAN umbrella. So people ask me, one of the other questions I get quite often is, why 5G IoT and why not use those other LPWANs? So let me go through my list of reasoning, and I'm sure audience, other people might have other points to make as well. So top of the first reason is, it is part of a very broad, big standards behemoth engine that's going to go on and on and on for a long, long time, but there's no end to this 3GPP standards body. It's a worldwide organization, hundreds of companies with intellectual property coming from worldwide sources. So that's a massive entity to be part of. It's very hard to imagine that standard setting organization not evolving their LPWAN in perpetuity, right? So that's one big reason to be part of it. Second reason is most of the other LPWANs tend to operate in unlicensed spectrum. There are a few exceptions, but for the most part, they operate in unlicensed spectrum. So what that means is that you have challenges in terms of quality of service, in terms of reliability, and to some extent, arguably, some of the security aspects as well. Just to compare and contrast with the 3GPP size and scale, most of these other proprietary technologies, other alternate technologies, are based on a single company owning and controlling the intellectual property and underlying the key technical specification, particularly on the physical layer sense. So there is a risk associated, there's a business risk associated with that going that route. So that is another big compare and contrast, because if you go with 5G IoT, and let's say, just again, putting a shameless plug for Puloli, so if you choose us as to implement a 5G IoT solution for you, and for whatever reason you don't like our performance 3, 4, 5 years down the road, you can always terminate the relationship with us and still bring in, I don't know, just to pick an example, Nokia or Ericsson or somebody else to come and do the same service for you, right? So you're not going to go dark, so to speak. Whereas if you're married to one of the semi-proprietary, semi-standardized other alternate LPWAN technologies, you're going to have challenges if they become a going concern. So that's the other major reason I state for folks who want to compare the NB-IoT Cat-M based solutions with other alternate LPWANs. And then the last point I want to make is that in terms of the actual characteristics and the performance of the network, when we talk about long range, we talk about indoor performance, we talk about supporting the type of use cases that are truly, can be battery operated and long lasting and all of that. This is proven. NB-IoT and Cat-M has been around for a while now. Cat-M more so in the US, NB globally has been proven and it's been continuously evolved and enhanced and improved. It is a proven quantity. So some of the other technologies has been a hit and miss depending on where you deploy, how you deploy it, and all the details behind it. And then very important to note is that the cost factor is becoming at parity. So for the first time now you can have an NB-IoT system that is a cellular quality, carrier quality, but essentially at a lower price point. That has never happened before. For the first time you have a 5G-IoT solution that can be deployed and operated at the lower price point. So the last remaining key differentiator that has been working in favor of LPWAN is also going away. So I just wanted to put all those out there because these questions come our way all the time or quite frequently, and wanted to highlight those. And the last point I wanted to talk about is that in order to get the full parity and at the price and at the cost point for the whole total cost of ownership at the TCO level, the last step is to have a fully integrated service. So edge compute is nice. We have Qualcomm and Sequans and others making very attractive price point for the chipsets for 5G-IoT. It keeps dropping every month. So that's all good. So you have very attractive economics coming up. And then on the network side, yes, you can, you have few suppliers on the network side who probably will keep on reducing their price point as well. But the key is making the applications and solution working end to end. And a lot of people, if you go to IoT forums and industry meetings and seminars, there's always this big question: why hasn't IoT taken off by the billions that everybody thought it would be by 2020 rolled in? Well, pandemic notwithstanding, but there was an expectation there's going to be billions and billions of devices out there. One of the dirty secret in the industry is that vertical integration, end-to-end integration. So never underestimate that. We run into this in many of our potential customers. They have, okay, somebody buys a spectrum. Okay, I have chosen a network vendor. I have chosen, okay, I want to go with the Qualcomm chipset. All good. Now, how is it all going to work together? So if you are as a utility, you have two choices. Either you can build a large organization, build in LTE, 5G, domain capability, domain understanding, and all the IoT domain expertise in-house, or you can hire a third outside system integrator. But one way or the other, it has to be integrated and optimized for that particular application and problem solution. Otherwise, you have a bunch of components, they work kind of sort of okay, but in order to realize the cost parity with LPWANs, other LPWANs, and realize the scale and the economics of it, you won't quite get there until you get that vertical integration sorted out. So that's an important point, and we see that increasingly becoming the determinant factor in success or failures of many of the IoT projects. So, so I wanted to kind of emphasize that, and then want to open up for questions. We are 40 minutes into the hour, so last 10 minutes, 10-15 minutes, I wanted to make sure we have some time allowed for the question Q&A. If you have any questions, so we have a booth in the exhibit hall. Come by us. There are 3 of us here in this conference. We can talk offline, and if you're interested in some of the end points, so we can show you what the next end looks like. And you can reach us info@biloli.com. So that's how you can follow up with us. So let me go back to some Q&A. So I want to go back to that gentleman. You had a question on the throughput. So you're talking about NB-IoT, Cat-M, or both?
Bandwidth.
Sure.
Both, okay.
Yeah,
So, yeah, so here's the thing. Now that I have explained the big picture, You never saw me talk about throughput, and there's a good reason for it. The reason is, at the end of the day, that is the fundamental difference between a broadband and IoT. In broadband, you should talk about throughput. In IoT, you don't talk about throughput. In IoT, what you talk about is that what type of application can I do and how many of them I can sustain. The reason is, it is not about sending a megabits per second streaming data. IoT is not for that. If that's your use case, if you want to have a megabits per second link to do an HD camera real-time streaming back to your back office from your remote asset, neither NB nor Cat-M is your solution. Then you need to have a EMBB or a LTE broadband or a 5G broadband set up at that asset location and to carry the data back. So yeah, if you ask me what is the physical layer link throughput, it's in the order of 100 kilobits per second for NB per 200 kilohertz carrier, and about 500 kilobits per second for Cat-M at the physical layer. This, depending on the coverage conditions and a bunch of other factors, but that link level throughput. That doesn't mean anything in terms of use cases. You can have tens of thousands of devices on NB-IoT, couple of few to 200 kilohertz carriers. If you do a telemetry profile, if you do the edge compute and the wireless link optimization correctly. However, if you want, just to repeat myself, if you want to do a sustained guaranteed throughput link, you need to go to the proper broadband. IoT is not your solution. I want to be very upfront about it because we get these questions all the time. We want to be very clear. This is something new, guys. IoT has to be used as IoT and broadband has to be used as broadband. Now you can piggyback some of the IoT on broadband. Of course you can do that, but the economics are very different. Battery life issues and all of that comes into play. But if you really want to have the massive machine type communication as 5G is intending this third leg to be, throughput is the individual link through individual connection, individual endpoint throughput is a non-factor. It is, well, in a sense, it is not the first thing you look into, right? I hope I'm answering your question in an indirect way. But if you are really looking for physical layer throughput, there is advertised rates that 3GPP has and other vendors have. It's in the in a couple of hundred kilobits per second for NB and 500 to 800 kilobits per second for Cat-M. Yeah. So sorry, before I go to the next question, did I?
Yeah.
Okay, we can talk offline too. Come by. There's a lot of nuanced aspects to throughput and latency when it comes to IoT devices. Yeah, go ahead.
Under use case one, I was
Mm-hmm.
just wondering, could you go back and tell me how you accomplished what you were trying to do there? And is there some function happening at the endpoint there, or is it just collecting all of the data?
This is a generation one, so what happens, the real edge compute is kind of not a heavy compute, but what's happening is that it is collecting the current loop measurement of the pressure much more frequently than what it's reporting. I think it's reporting either 5 minutes or 15 minutes, reporting back to the cloud, but it is measuring more frequently. So it is not the best example. This is 2 years ago, so it's not the best when we deployed it. It's still operational, but it's deployed 2 years ago. It is not the best example of all the things you could do on edge compute, but there is the platform is edge compute. It's a microcontroller with a MicroPython as a development environment. You can write many applications and many micro applications to do various edge compute. What's deployed is somewhat simple, but it has the potential to do a lot more. Any questions, Kevin, on the online?
Oh, no.
Nothing yet? Okay.
No.
Any other questions on either use cases or the generally 5G IoT, broadly speaking? Yeah, Bob.
I'm going to ask a question. We heard yesterday from a utility they're putting in a broadband LTE network and going to put 20 different applications. It's conversion, 20 different applications on that. So I don't know if you can speak about this. I'm going to guess that some of those would be perfectly adequately handled on an NB-IoT network, but they're putting them all on the broadband network. Do they gain efficiency, lose efficiency doing that way? Is that something you could address?
They'll gain and lose. Some of the things they'll gain, the other places they're going to lose. So where they're going to gain is that anytime they have an NB or a Cat-M in band, in the generally broadband LTE spectrum, channelization, that is a gain, right? So you can still implement a lot of the NB-IoT power management and optimization that way. What they're going to lose is that if they have to do a longer range, because LTE broadband doesn't have the same range on the side. So if to the extent they need to have a lot more remote devices, a lot more indoor penetration, they need to over-engineer the LTE side, so to speak. So that increases the cost basis of it. So that's where they lose it. So you can, I mean, it's very difficult to have the cake and eat it too, right? So you need to trade. So they will have they have to make some trade-off decision there. The other thing they could look into is to have a narrowband system and a broadband system coexist, where you can completely segment the you have an NB-IoT or a Cat-M system for for the kind of use cases we talked about, and then have the broadband still served, potentially could be served by the same entity, implemented by the same provider, the same vendor of choice. So that's a possibility, but. From what I understand, from my understanding about having broadband and Cat-M NB all combined, is that you're going to miss out on some of the coverage challenged devices and remote devices that are further outside.
So as a spectrum seller, right, we can encourage them buy a separate frequency, right, maybe 700 to handle NB. Get the range, get the coverage, get all the benefits without sort of making your broadband system more complex or more expensive.
Yeah, that definitely, we had that conversation within a couple of places now. Whether that's going to come to real world implementation, I don't know, but it is definitely feasible. Definitely, both technically and economically, I guess it makes sense. The big aha moment we see when we explain this to folks is that many of the use cases they thought they're going to need broadband, when we explain what can be achieved with the edge compute combined with the NB-IoT kind of spectrum, that covers 90% what they thought they're going to need, and okay, some 10% of the use cases they still need a kind of a broadbandish spectrum and network, but they are very pleasantly surprised to see 90% can be done this way. If you do, the key is you have to do edge compute, and you need to have this fully integrated solution. If you just buy an off-the-shelf, I'm repeating myself a little bit here, if you buy an off-the-shelf NB-IoT Cat-M module without any optimization and put it into the network, it won't have the optimized traffic profile, optimized edge compute to reduce and protect the radio link, to use the radio link efficiently. So then all your calculations about device density and usage and range, all of that, now no longer valid. So yes, you can do a lot as long as you do the proper end-to-end design and optimization of the application the right way.
All right.
Any other questions? Last call. Okay, yeah, go ahead.
So you mentioned a lot of the sectors.
You may want to wait for the mic so that the folks on the webinar, the online could also hear, please.
You mentioned a lot of the sensors are battery powered, so I'm just wondering, is there any standard or typical pulling intervals to try to extend the battery life on these sensors?
Yeah, standard in terms of best practices, you mean?
Yeah.
I am not aware of a lot being published, but it is a lot of learning going on right now by various key players, us one of them. It also depending on whether you want to do a current loop based sensors or if you want to do I2C sensors, and then that also makes a huge differences in terms of what's possible. Because current loop is very challenging to do on a pure battery only solution, whereas if you can do on a more I2C or some other more current battery optimization feasible options, then that makes a huge difference, right? So I think migration towards, this is strictly my personal opinion, I think the there are a couple of guys who really know better than I do in the audience. Go far, come by our booth. They'll be happy to give you a lot more insight. But I think my high-level take on it is that if you go towards an I2C kind of implementation, that becomes very possible. That will be the best guideline I can give in moving away from current loop where possible, as long as the environmental and regulatory framework allows the utility to move away from that sensor to an I2C sensor. I think that will be a first step.
I think we have time for one more question.
Yeah, go ahead.
Okay. Could you comment on the differences in range between broadband and IoT?
So between broadband and NB-IoT, I can give you the answer in terms of link budget differences. I believe it's close to about 20 dB or so difference. So LTE baseline is about 140 something, MCL maximum coupling loss, and NB is 164. So there's about 24 dB difference, I think. So that translates into distance. I mean, if you you can translate that into a distance based on which frequency band you're deploying. So that gives you quite a bit of range. So for example, I mentioned 25 miles, 40 kilometers that we have verified in terms of NB-IoT on a 700 megahertz spectrum. LTE doesn't even come close to that, obviously, at the default link budget, default LTE model. So it's quite a bit of range, and also, again, I'm not an expert. These two gentlemen in the audience can tell you later on, but there is an extended range specification for NB-IoT coming on in this release or the next upcoming 3GPP release that will probably double the distance that can be reached through NB-IoT. So that's further, and as far as I know, LTE baseline or 5G-NR baseline does not have that capability. So you're talking about a very long distance coverages as long as the link budget and the power levels and the capacity of the carrier can sustain that. So I don't know, I answered your question. I'm kind of an indirect answer because just like most of these questions, there is no simple, yes or no or binary answer to these things, unfortunately. That's the way physics works. But hopefully give you some idea. Any other questions, please?
I think that's all the time we have for questions.
Oh, okay,
So
all right,
maybe
yeah.
another booth to talk to you guys forever.
Okay, yeah, come find us later on offline. Yeah, thank you.
Thank you all
Thank you very much.
And